Okay, so we're going to finish this section off with a couple of formulas. And before I write them down, I just want to really make sure it's clear what they're actually doing or where they came from. So we'll just read this note carefully. The foregoing process, that just means the process that we went through immediately before this, may be applied to a general point P and a general line ax plus by plus c equals 0. Right? This is a general equation of a line in R2, or one way to write it, to yield a formula which calculates the distance between a point and a line. In other words, any point in any line. So what that's saying is really this. Imagine if you went back to this example. Imagine if we just, instead of using this line and this point, imagine if we just replace the point -1, 4 with just a general point P x naught y naught, and then replace this line L here with the general line ax plus by plus c equals 0. And then we just did all the exact same steps. Well, what would that look like? We're not going to do it in detail, but let's just run through what it might look like. For the first step, when you choose your point Q that's on the line, well, this won't necessarily work anymore, right? You'd have to choose, where's the other page? You'd have to choose a point on this line. So the coordinates you use, well, it's going to depend on A, B, and C, right? So when you go to choose your point Q, the coordinates of Q are going to be dependent on A, B, and C. So you won't have a specific point, you'll have an unknown point that depends on these fixed constants A, B, and C. And that's okay, that'll make things more complicated, but you can still do it. Then when you go to form the vector U that goes from Q to P, well, P, remember P in this case is the general point x naught, y naught now. So your vector U is now going to be dependent on A, B, C, and x naught and y naught, which are all fixed numbers. So technically you could still form that vector. But now there's going to be a lot of unknowns floating around in your vector U. And then similarly, when you go through the process and finish all the rest of the steps, when you finally find that you're going to have to find the direction vector of the line here, which again, that'll be dependent on A and B. Then when you compute the projection, it's going to get quite complicated. When you compute the projection W1, you're going to have A, B, and C, x naught and y naught, y naught, all floating around in the coordinates of your vector W1. And the same when you go to calculate W2 and do the subtraction. So when we finally get to this stage, there's going to be a lot of x naught, y naught, and ABCs floating around here. So to take the norm, it's going to get a bit complicated. But in the end, the process will still work, and we can still calculate a distance, the norm of this W2 vector, and this is where your answer came out. Right? So at this stage, this presumably should be dependent on A, B, C, x naught, and y naught. So it would be technical, but you could do it. You just have to take your time and go carefully and give yourself lots of space. But what do you think would happen if you did that? What you would have in the end is a formula that allows you to just simply plug in the coordinates of your point P, and then plug in the coefficients and the constant term of the line, and then what you'd have in the end is the distance between the point and the line. And you wouldn't have to go through that 5-step process ever again. That's really what doing that would get you. Now, we're not going to do that, but I am going to give you the formula that you would get if you did do that. So here it is. The distance in R2 between a fixed point P, which is given by x naught, y naught, and the line, which is written in this form, is given by the following. So it's given by, I'll call it capital D for distance. So, and before I write down the formula, let me just tell you out loud in a couple of steps really what I'm doing and how I'm getting this formula, and it makes it a little bit easier to remember. So it's going to be a fraction, and the numerator you can get by just taking the point P and plugging it into the left-hand side of this equation. Right? So take x naught, plug it in for x, take y naught, plug it in for y, and then whatever you get from that, you'll just write on your numerator. So you have A x naught plus by naught plus c. That's the numerator. But then just put an absolute value sign on it. So you have to take the absolute value of the result. So work this out first and then take the absolute value. And then the denominator is actually, really, you can think of it this way. Just write down the normal vector of the plane, which is going to be the vector AB, and then take its norm. Plug it into the norm formula. So you get the square root of a squared plus b squared. So that is your formula for distance. But just be very careful. You need to make sure that the line is written in this form. Quite often, you'll be given the equation of a line in some other form. Maybe the constant c is on the other side of the equation. Well, if that's the case, you better subtract it over to the left-hand side, and then it may have a negative sign built into it as a result of that. But that's okay, you can still use the formula, you just have to convert your line so that it's written in this form. So that is your distance formula. Okay, and an analogous problem in three-dimensional space is, we didn't ask this question, and we're not going to look at it in too much detail, but there's a formula for it as well, which I also want to give to you. So the distance in R3, so we're talking about the distance in three-dimensional space now, between the point, this is a fixed point, but now it's got a third coordinate, z0, and a given plane, which is written in this form, ax plus by plus cz plus d equals 0. So a, b, c, and d are just constants, and x, y, and z are the variables. So there's a formula for this as well. So let me just draw the picture before I give you the formula, just to make sure it's clear what we're actually talking about here. I'm not going to prove this to you in general, and we're not going to look as deeply at this problem, but since it does have a formula that's so similar to the one we just wrote down, I do want to include it with this theorem. So let's say you've got a plane, and you've got some point not on the plane. Right? It makes sense to speak of the distance between this point and this plane. Right? What you would want is you'd want to get the shortest possible distance. So that this point down here, if you picked any other point in the plane and formed the vector to that other point, you would get an orthogonal vector, or an orthogonal angle, or pardon me, an angle of pi over 2 between this line segment and whatever line segment you formed by choosing this point along with one other point in the plane. Or you can phrase that in terms of orthogonal vectors, but it doesn't need to. So what I'll do is I'll just write that square just to indicate that. So the idea is this line segment is parallel to the normal vector of this plane. Or you can, some people would use the language, this line segment is orthogonal to the plane or perpendicular to the plane. I didn't actually go into too much detail on which exact words you're allowed to use in those contexts, but I think it's intuitively clear what that means. But if you want it to be really formal, then I could say the following, which I'm not going to require you to do. But take a vector that has an initial point here and has a terminal point somewhere else in the plane, and then take the geometric vector that goes from this point to P, and those two vectors will be orthogonal. That's what it means to write this little box here. Okay, so really what you want is you want this distance here. Okay, and that is what this distance is referring to here in this statement. So that's the only thing I want to make absolutely clear. So the distance in R3 between some fixed point given here and the plane ax plus by plus cz equals, plus d equals 0 is given by the following formula. And it's almost identical to the way it's laid out here, right? But it is slightly different. So the distance is given by the following. And it's the same idea. Just take this point, plug it into the left-hand side of this equation, and that will give you the numerator. So ax naught plus by naught plus c z naught plus d. And then again, you're going to take the absolute value. And then all of this is going to be divided by the norm, or the length of the normal vector of this plane, which is given by the square root of a squared plus b squared plus c squared. Okay, so that's the formula that'll give you the distance between a point and a plane. Okay, where it comes from comes from a similar approach. You end up needing projections to do it, but I won't go through that one in detail. If anyone wants to discuss it, I'm happy to do that.